Hello, everyone. I'm sorry today is a slow internet day, but I also learned something rather fascinating. I will explain this as we go, waiting for people to join in. We're up to 15 now. It's a pretty good fraction. Well, it turns out Zoom's not a time machine because I just logged into Zoom to do my 12:30 class, and it appears that they weren't there just because it's 11 o'clock. So so yeah, I'm that idiot who went to the wrong Zoom classroom. I've actually done that before with the wrong physical classroom. I walk in there, I'm like, "Who are you? I don't recognize any of you goobers." I realize I'm the idiot that's in the wrong room. But anyways, that's what happened. Do any of you folks have any questions before we get cracking?
Just a quick lab question, just to verify the assignment is due before the next class or before Thursday, correct?
Which assignment's that?
Lab 2.
Oh, lab 2. Yeah, it's due at the beginning of your lab time. So if your lab meets at 1 on Thursday, it'd be at 1 o'clock on Thursday. Scared me. I thought you were talking about the homeworks. I do have to reset the dates for instance, we start chapter 24 today, so I have to set those dates. They might not be right. As a bare minimum, they should be due Sunday of this week. But if I have any problems and can't finish chapter 24 by then I might move it back. Sometimes I might put the concept questions due Sunday and then the actual problems due Wednesday. That might make it a little easier on you guys. Anything else, anyone? So last time I think we finished the chapter on voltage. Again, I don't try to cover necessarily every little example. In fact, I usually make up my own examples. Very seldom do I use their examples, or I use an example that's a lot like theirs, but there's a finite number of problems we can actually solve. So we have to sort of overlap a little bit. That being said, you still are responsible for all those examples. So make sure y'all keep that up. Today we're going to go ahead and start chapter 24, and that's on capacitance. And just like last chapter was on voltage, but I repeatedly got to use Gauss's law, which was the previous chapter. Well, in the capacitance chapter, we're going to repeatedly use the voltage equation, and in fact, we can use Gauss's law to ultimately determine capacitances. So one of the big things we're going to introduce is this concept of a capacitor, and we've already sort of hinted at it several times when we took that infinitely large plate, maybe laying horizontally, that had a surface charge sigma. And I used Gauss's law by, creating a Gaussian pillbox or soup can that sort of sandwiched, if you will, some circular area of that plate. And then I used Gauss's law to calculate the electric field at the top plate and the bottom plate. And of course, the side plates had no flux because the electric field was perpendicular to their surface vectors, which pointed this way. And what we found was, at least for an infinite plate, the electric field was uniform. It was actually didn't depend on R at all. It was just sigma over 2 epsilon naught. And then when we put one positive plate next to a negative plate, the positive plate tended to push positive charges that way. So that means this electric field will point that way. But the negative plate tended to pull negative charges to it, so it went that way as well. So when you add them two up between, you get sigma over 2 epsilon naught plus sigma over 2 epsilon naught, which gave us sigma over epsilon naught. And that turns out to be the electric field between two parallel plates, assuming you're not that close to the edge. Then we did the electric field mapping, and I think you were able to see that basically the equal potential lines were essentially parallel to what you considered plates when you put those charges along there. Those equal potential lines being parallel to the plates meant that the electric fields were perpendicular, of course, to the surfaces of the electric plates, as well as to the individual equal potential lines. So you saw a uniform electric field. If it wasn't uniform, changing from one equal potential to another equal potential, which maybe was 1 volt, if you went the exact same distance from that one to this one, that volt would be different. It'd be like 2 volts or 3 volts or something like that. That would indicate a electric field that was differing in strengths. This one didn't. It went all the way across. And then, of course, when you got to the edges, it was doing all sorts of crazy stuff, curving this way and that way. Well, that object, those two plates close to each other and charged, with a vacuum in between it, or even with a dielectric, which is a really cool fancy word for non-conductor, that is called a capacitor. And if you learn a little bit about them, you can sometimes save yourself a ton of money. I've saved quite a bit of money, not necessarily safely, mind you. I could have been killed on any of those instances. So, for instance, I once bought when I first got a really kick butt engineering job. I was working as electrical and software engineer. I was writing code as well as using my knowledge of electrical engineering, CMOS, and that sort of stuff to work on software and write software that was designed to allow people to create integrated circuits. And in that job, it was an awesome job. Let's just put it that way. But in that job, one of the things you had to do was understand all this different electronics kind of stuff. So when I did that, I was making a ton of money, and they had just come out with HD TVs. And because I was making a ton of money, I had no expenses. I even had my wife and my new child got to stay at home because I was making so much money and had so many wonderful insurance policies and all that good stuff. I bought a new car, I bought a new house. And in fact, I went out and bought at that time, I think it was a $6,000 TV. It was a HD TV. Well, that in 2000, $6,000 TV was a 45-inch, and it was a big box. It was narrower than the big box old projection and inner projection TVs that we have even today, or even just 5 years ago. But it was super nice, and I really loved it, and it was working fine for years. Well, then 9/11 came along. I got laid off, and still had that nice TV. Luckily, I was able to work at Home Depot and make ends meet and stuff like that. But all of a sudden, that cool TV that I paid so much money for, one day I go to turn it on, it goes. I'm like, what the heck? And I was mad. I had since bought different TVs, but that was the TV my girls went into the playroom and played video games on and watched movies when they didn't want to watch what we were watching. So I was like, let me get somebody to fix it. So I called the beach repair guy, because I live in Currituck. And he said, yeah, we can fix it. It's basically, I'm going to charge you $150 to come pick it up. Okay, I'll bring it to you. Skip that. All right, well, I'm going to charge you $150 up front just to find out what's wrong with it. And then I charge you $75 an hour for whatever labor I have to put into fixing it. And then, of course, you're also going to pay for parts. And I was like, damn. Right? I was like, that's a little expensive. So I said, okay, well, I'll get back with you. And I opened it up because I have, some electronics experience. And lo and behold, I looked right there on the circuit board. First thing I did was before opening it up is I unplugged it. That's a very good thing. But believe it or not, that's not good enough. That's why I'm warning you guys, you can die. Okay. Even with it unplugged, you can die. So when I looked and there was this capacitor, and a capacitor normally either looks like a pill that's been squished at the edges. So it's like sort of like a Lunchable. If you've ever seen those Lunchables, it looks like a Lunchable, only it doesn't have those fancy little pleats around the edges, and it's got two little wires hanging off of it. That's a typical capacitor. Also, some of them look like little cans with two little wires sticking out of them, and the wires don't stick out of opposite ends ever. I mean, hardly ever. At least I'm sure there's some design where someone's done it. But the one I had seen was, in this case, was blue, and it came down and then got narrow and then came down again, and then that was the bottom. And on the top, it had a aluminum sort of Mercedes symbol, aluminum top on it. And I looked, and sure enough, that Mercedes symbol went pop. Whenever you see that, your capacitor's busted. Just so happened that because I taught basically an honors 242 class at Chapel Hill, we went through this process where we taught people how to make basically a microwave antenna, and we did it bit by bit, teaching them electronics. So I had all these cool tools and all these extra parts, and I looked, and it happened to be exactly one of the capacitors that I had from that little kit. So I snipped it off, and mind you, the capacitors are the danger. So when I tell you, just because it's unplugged, you're not safe, it's the capacitors that often are that problem. Okay, because sure enough, when I went to solder it back, my screwdriver hit a different capacitor and a heat sink, and sort of welded the screwdriver to it. And that was, if it was enough power or amperage to weld a screwdriver to a heat sink, then you can be assured that was enough to kill me. So I really got lucky on that. But lo and behold, I clipped that little thing out, soldered it back in, worked beautifully. Same thing happened with my HVAC unit. It wouldn't crank up. Someone said, oh, you just need a new unit. It's 15 years old, blah, blah, blah. Well, I looked, and actually I looked around and talked to people that did HVAC work, and then I Googled some things, and I found out that often it's just what they call a start capacitor. And I said, well, let's check that out. And I looked, the start capacitor was bad. I could tell that. So again, carefully, because again, a capacitor can hold all that charge even when it's unplugged. I carefully removed the thing and bought exactly that capacitor for like, I think it was $25. I bought it from Ferguson. And then there was another problem in that I'm not an HVAC guy, so I don't really understand multiple capacitors in one setting. So it took me a little while to figure out what all the plugs were, but that literally had like two, sometimes they have even more capacitors in one. So once I finally figured out how to connect it, I connected it and it worked perfectly for another 2 years. In fact, I'm only now replacing it. That was 6 years ago. So anyways, this can help you a lot, just knowing this basic electronics and knowing what capacitors look like. Your book on page 628 has some photographs of the various types of capacitors. You'll even see in the top right of that photograph, you'll see these little plates. They're sort of like semicircular aluminum plates all laid along each other like this. Okay. And then there's another semicircular aluminum plate on an axle that goes through the middle of those semicircular plates, and you can rotate that, and basically the amount of the semicircle that overlaps with the semicircles at the bottom increases the capacitance. And that's exactly how your car stereo tunes into a particular radio station. It has a what we call a waveguide, a resonance type cavity type thing, where basically the electromagnetic radiation oscillates just perfectly for a certain wavelength. And you can adjust that by adjusting the capacitance. So that's some of the cool things that capacitors do. You can see, in fact, that 2200 microfarad 35 volt capacitor, that looks almost identical to the capacitor that I pulled out of my TV, only it was one that had two wires poking out of one end, like the little one beside it. Mine was 1500 microvolts though. So anyways, and it had a certain temperature rating, which mine I already had to as well. So I got lucky. But that's what a capacitor is. And really what we use it for is sort of like it's the best battery you ever had. Okay. So it can store a buttload of electricity, a buttload of energy, if you will, which is really what it's storing. It can store a buttload of energy, and it can deliver it, bam, light and fast. Batteries can store a lot of power, a lot of energy, not power, but energy. But they can't deliver it so fast. And in fact, however long it takes to deliver it, it takes about that long to refill it. That part's also true about capacitors, but capacitors can be drained really quickly. So for instance, the first uses of them that I ran into, other than stuff that you'd have to look inside of circuits to figure out, was an obvious use when my mom got her first 35 millimeter camera. You would take a picture with a flash, and then you hear, and it would raise and pitch as it's going. Well, come to find out, they don't use batteries to run a flash cube because you need the power delivered right then, right? So what they actually use is a capacitor, and that was that humming noise was a noise they put in to let you know when the capacitor is actually full. So a capacitor is normally what drives, for instance, flash cubes or flashers on, well, flash is probably not the word I meant, but anyways, the flash device on a 35 millimeter camera and other photography type stuff. One way you can actually make them is you could just take two parallel plates, and then you will see in a few minutes that the capacitance, which is the important parameter about a capacitor, really is improved by increasing surface area. So the bigger this plate is, instead of using something the area of my hand, maybe you use something the area of a football field. That would be a really, really big capacitor. And then it's also improved by bringing them closer and closer together, which you've already learned that, if you fill the gap between the plates with air, there's going to be a point where the voltage is high enough for lightning to strike across it, and your capacitor has failed. So that's a problem. Not only that, if you're taking two plates, even if you let's say make them out of aluminum foil, when you charge one positive and charge the other one negative, they're going to be attracted to each other. So if they're not really rigid, they're going to go against each other. And again, you've got a failed capacitor. So it turns out it's a bit smarter to actually put a dielectric, again, a non-conductor, in between the two plates. And then you can take the two plates and roll them up like a cigarette, and then encapsulate them with some plastic, and you'll get a big area in a small place. And that's what those little round ones look like. So that's what your book's showing you on the top of page 629. They're indicated on a circuit by either two parallel lines. So a wire comes in, there's a vertical line, and then a parallel line, and then the line comes out. Or sometimes they'll have a curved line on one side, and that means it's what we call a polar capacitor because it has a specific way you have to connect it. If you connect it the other way, it'll burn it up. So just be careful of that. So let me introduce you to what capacitance is. You can see already the name of the chapter is Capacitance, Dielectrics, and Electrical Energy Storage. And that really is what capacitance is used for. So let's turn on my document cam. Anybody have any questions on that before we move along? Okay, I'm gonna turn on my document cam. And what we're gonna define capacitance as is basically the amount of charge you can hold for a given voltage. So I often just say capacitance is equal to charge over voltage, but you'll notice your book is really just saying that the charge is equal to the capacitance times the voltage. And both of those obviously are valid equations because you can manipulate one to make the other, right? Now, what this tells you is that the unit of the capacitance, C, notice I put a square bracket in it, that means dimensions or units. So in this case, we're going to see it's basically called 1 farad. And that's written 1 capital F. Okay. Now a farad is defined to be 1 coulomb per 1 volt. Now a farad's a big unit. Okay. Just like the coulomb's a big unit, the farad's a big unit as well. So if you have a 1 farad capacitor, it's a dangerous thing that could bite the poop out of you. In fact, when you see a capacitor lying around loose somewhere, your first instinct is should be to not touch it because it could be a collected charge just from being in a room. And if it's a 1 farad capacitor, that's enough charge to deliver an amperage that could kill you. So you don't want to mess around with it. Ideally, when you leave capacitors laying around, you're going to connect a wire to the 2 terminals. So for instance, that capacitor I was talking about earlier that I replaced looked like this. The dimensions aren't, the ratio of the dimensions aren't quite the same. It was a little more elongated than this would have you believe. Okay, and you had the wires would come out like this. If you just take a wire and tie it around this end and tie it around that end, then you're going to keep it from actually causing a problem. So that's a typical capacitor. The other one I was mentioning kind of looks like a Lunchable with pants on. So here's a Lunchable with little pants on. That little belly sort of thing. And the wire comes out like this. See, doesn't that look like a Lunchable with pants on? No, not Lunchables. What are they called? The little sandwiches, not Lunchables. They're called.
Oh, I know what you mean. The peanut butter and jelly sandwiches.
Yeah, the peanut butter and jelly sandwiches. Dang, I can't
Yeah,
remember
the
what they're called.
prepackaged ones. I think it starts with a W.
Yeah, man,
sure.
I love those things. They got the best bread and everything. But anyways, it looks just like that. But look, he's got pants on. So that makes me laugh a little bit. So we now see that the capacitance is really defined as the amount of charge it can hold per unit voltage, if you will. And the more typical units that we use are the microfarad and the nanofarad. But occasionally we also use millifarads and actual full farads. Those are all fair game. Remember, you need to know your SI prefixes.
Don't they typically, like for high farad capacitors, they call them super caps or super capacitors?
Repeat that, I missed it.
For high farad capacitors, don't they typically call them super capacitors to like differentiate them?
Yeah, sometimes they do that just as an extra name, and it also gives you a warning about not to do it. I remember the name is a crustable. So I wrote it up here so everybody would know. It's a crustable with pants on. Okay. Yeah, super capacitors. And in fact, you can look on YouTube, you'll find a guy that works for NSF, and he makes a 1 million capacitor. I want to say he makes a 1 million capacitance capacitor, and he uses some really awesome, expensive capacitors and puts them in a huge bank. And you can do that, for instance, if you wanted to make a Tesla coil without a lot of the other contraptions. You can just make a buttload of a bank of capacitors, charge that sucker up, and it'll fire lightning just like a Tesla coil will. So Google cool things with capacitors if you want to see what it is. And we use it a lot more than you think. Keystrokes, when you punch your keyboard, that's often a capacitor. We use capacitors as memory because when they're charged, you can count them as a 1, and when they're not charged, you can count them as a 0. All sorts of cool stuff like that. What we do know is that for a parallel plate capacitor, we've calculated this already. We know that for a parallel plate capacitor, the electric field inside is the charge on the plate over the surface area of the plate times epsilon 0. Remember, it's sigma E is equal to sigma over epsilon naught. That's actually what the electric field is. And since sigma is the surface area is the charge of the capacitance divided by the surface area, then Q over A is that. So we'd say this guy might be the positive side, this guy would be the negative side. The main thing is the two charges Q will be identical but opposite in sign. So that's a typical capacitor. Right? Now, using that, we can actually calculate, remember V, or delta V, equals VB minus VA, or equals V final minus V initial, is equal to the negative integral of E dot DL from A to B or I to F, whichever one you want to do. So what I'm going to do is I know the electric field actually points this direction, right? And I know specifically that this is the higher voltage side, so I really want to get a positive out of this. And that helps you learn more about voltages by always trying to do that. But be advised, if you ever do this calculation to calculate capacitance and you end up getting by accident a negative, just throw the negative away, okay? So I'm going to say that that is equal to the negative integral of E dot DL. So I'm going to write the negative here, and I'm going to take the integral. And I'm going to take the integral. Let's let the direction of the path be dictated by the DL as opposed to the range of integration. So I'm going to set this, for instance, in a coordinate system where X is that axis and Y is that axis. And the separation here, of course, is D. So this would be X equals 0. That's X equal D. Okay. So I'm going to choose the DL to choose my direction. That means the range of integration just has to go from low X to high X, which happens to be the same thing in this case. So I'm going to integrate from 0 to D. My electric field, on the other hand, will be Q over A times epsilon naught in the I hat direction. And my DL, which I'm going to actually integrate from, I want to go from low to high. So in fact, I want to integrate from this side to that side. That's my hypothesis, right? So I'm thinking that should give me a positive quantity. So I'll take the negative dx, the negative indicates the direction I'm going, times I hat. Okay. Well, you can see that I hat dot I hat, because that's a linear operator, you can pull the negative dx, the q over a epsilon naught. They can all go in front of the I hat dot I hat, and I hat dot I hat just becomes 1. So I ultimately get plus, now the q, a, and epsilon naught are also all constant. So I'll put q over a epsilon naught out in front of the integral. And now I just have the integral of dx from 0 to d. And I think you can all see that that is ultimately q d over epsilon naught a. So that's the voltage difference. And it did come out positive. So I did my line integral properly. I wisely chose the direction so that I did get a positive quantity. So that's something you should try to do every time, just to make sure you know how to do line integrals and to make sure you understand voltage pretty well. Does anybody have any questions on that part? Now, remember, I could have started off with just one plate and did Gauss's law to come up with Q over 2A epsilon naught, and then worked out the situation that the two electric fields from the two different plates are adding together to give you the total Q over A epsilon naught, and then went with this. But I didn't do that. I'm just starting with the electric field. And we know that capacitance is equal to Q over V. It's the charge the capacitor has divided by the voltage across the capacitor. I just calculated the voltage across the capacitor. So I'm going to take the Q and divide it by QD over epsilon naught A. And I think you can see what happens. The Q's cancel out. And that should always happen, by the way, when you use this definition of capacitance. You should ultimately get a capacitance that only depends on the geometry of the capacitor. So in this case, we're going to get epsilon 0 times A over D, and that is in fact the capacitance of a parallel plate capacitor. So C, parallel plate capacitor, is equal to epsilon 0 A over D. So that's a new expression we just derived. And that is one of the goals of this chapter, is for you to be able to take an electric field, or maybe even start without the electric field, using Gauss's law, create an electric field, calculate the electric field, and then use that to calculate a voltage between two parts of a capacitor, and then finally use Q over V to calculate the capacitance of a particular object. Okay. So let's consider another object. Let's consider, for instance, well, first off, does anybody have any questions on that? Now, to calculate that, you could actually put in some numbers. For instance, you could say, well, what size surface area would you need to make a 1 farad capacitor? So let's do example 1. Consider trying to make a 1 farad capacitor that is air / vacuum filled and made of parallel plates .00 millimeters apart. So what we're going to do is we're going to attempt to calculate what surface area would it have to be. Okay. What must A be? I'm going to assume this 1 microfarad, or this 1 farad, is 1.00 by the way. So I'll say 0.00. Okay. So I know that capacitance is equal to epsilon 0 A over D. So really A has to equal C times D over epsilon naught. Well, C is going to be 1.00 farads. D is going to be 1.00 times 10 to the negative third meters. And then epsilon 0 is going to be 8.85 times, let me make sure I did this right. A would be CD over epsilon 9. Okay, 8.85 times 10 to the negative 12th. And that one turned out to be Coulomb squared per Newton meter squared, which you could also put in volts per meter relationship. That would be actually a nice way to do it, to make your life a little easier. So A is going to turn out to be 10 to the negative third divided by 8.85. So 1 e negative 3 divided by 8.85 e to the negative 12. And I get 113.0. That's one extra sig fig with that 0 there, times 10 to the 6 square meters. So we're talking 113 kilometers by 113 kilometers. So yeah, a 1 farad capacitor is something that's not that easy to make. Now notice the capacitance goes up the smaller the D is. So using 10 to the negative third was actually helpful, right? But using 10 to the negative third also meant the area had to be even larger. So that's where the downside of that is. But yeah, even at 1 millimeter, which remembers about the thickness of your fingernail, well, at least of a funky fingernail, there's a millimeter, there's little marks on the centimeter side. So that close together, imagine having something 113 kilometers by 113, or excuse me, 113 kilometers by 1 kilometer, I guess would be sufficient. Or excuse me, yeah, that works. Kilometer be 10 to the third, another kilometer be 10 to the third, 10 to the third give you 6. Yeah, 113 by 1 kilometer would be big enough. But imagine them only being a millimeter apart, how hard you would have to keep that and build that to keep them from running into each other. So that's sort of what you get from trying to make a 1 farad capacitor. You can see that to do so requires a very small distance or a very large area or some combination thereof. You can also use that, of course, you can use the expression we found before. For instance, we found that the voltage turns out to be the electric field times the distance. That is, in fact, exactly what we found here, because remember, this is the electric field. So with that in mind, you can say this is actually equal to the electric field times the distance. And that's only true in a uniform electric field. But that is something we can use over and over for such a situation, but only for such a situation. So that's another equation that comes in handy. So if they give you a problem, like you can look at example 24.1. So you can see how they can give you certain information, and then you can use that to solve for other things. Like in that case, they gave you the calculate the capacitance of a parallel plate capacitor whose plates are 20 centimeters by 3 centimeters and are separated by 1 millimeter air gap. Then they ask you what's the charge on each plate if a 12-volt battery is across it. And then they ask you what is the electric field between the plates, and D, they estimate the area of the plates needed to achieve a capacitance of 1 farad. So they did something similar to what I was doing, only they followed a bunch of other stuff. So now that you have this, you could say as a follow-up question, well, what would be the voltage, or excuse me, what would be the charge in this capacitor if I connected it to 12 volts? And what is the actual electric field strength? Would be another thing we could do. So those are all calculations you can do, but I think they're trivial enough that, I would certainly take the time to work them in a physics 202 class, but I don't usually worry too much about it in a physics 242 class. You can see those examples on your own. But what I do know that students have a problem with is applying it to, say, a capacitor of a weird shape. So let's imagine this. Let's imagine a capacitor that has an inner cylindrical wire whose radius is, let's call it R1, and it has an outer cylindrical shell whose radius is R2, okay? And that's just a shell, so it's really, really thin. But it is a cylindrical shape, not a disc. So this thing you can sort of consider going on for infinity, like that, okay? But let's imagine just a length L of that capacitor, okay? What I'd like to do, assuming there's air in there, is I want to calculate the electric field between it and then calculate the capacitance. So my goal is to, well, actually, I don't need to do that. The capacitance. of this object. So that's what I'm wanting to do, calculate the capacitance of this object, okay? So first thing I'm going to do is imagine that little length L. I'm going to create a Gaussian surface to treat the electric field, or to find the electric field between the inner and outer cylinders. Okay, so this Gaussian cylinder has that same length L that I talked about, and it'll have, in fact, a radius little r. So left-hand side of Gauss's law says the closed integral of E dot dA. Well, obviously I chose this for an end. Now you notice you're going to have an end cap here, but by the symmetry of the object, you know the electric field is always going to point radially. So I would imagine, for instance, a coordinate system, I would imagine Z going right along the center of that innermost circle, X and Y being in the plane of the end. And then, of course, the dA on this side would be in the k hat, or in the negative k hat direction. And on this end, the dA would be in the positive k hat direction. And of course, the electric field is always in the XY plane, meaning it has no k component. So when you take the dot product, this becomes 0 for the bottom and for the top. So all you're left with is the little dA you get right here, which I'm going to call dA is equal to dA. Let's call that r hat, even though I'm using the cylindrical r hat, not the spherical coordinate r hat. Okay. My hypothesis is that E of r is E is equal to some E of r hat. So that's what my hypothesis is. I know I've already got two terms that are 0 because of that. Plus I have the integral of E of r hat dotted with dA r hat. Of course, r is the radius of that object, and the electric field, of course, is a constant on that object from the symmetry of it. So that just comes out in front, and I get E of r times the integral of dA. Remember the, actually I don't need that anymore. Remember the r hat dot r hat just gave us 1. The integral of dA, of course, is going to be 2 pi r times L. That makes sense? Now, if we assume
R1 or R2?
That's actually just plain R.
Just R.
So R is, yeah, because it's on the surface of the Gaussian surface, which was that radius, that cylinder that had a radius R. Okay. Now the right-hand side is really easy. So I'll write it over here, right-hand side, Q enclosed over epsilon naught. Now we assume this was uniform. Uniformly charged, so that lambda is actually equal to basically Q over L, where Q would be the total charge. Does that make sense? So Q enclosed in this case is just going to be lambda times L and then over epsilon naught. So that's the right-hand side. So this means left-hand side equal right-hand side gives me E of R times 2 pi RL is equal to lambda L over epsilon naught. You can see the L's cancel out, and ultimately you'll find that the electric field is equal to lambda over 2 pi epsilon naught times R, pointing in the R hat direction, and I'll write CYL because that's cylindrical coordinates. So that's the electric field. And of course, we already knew that. We've done that 1,000 times, but that's the electric field between the plates. I could soup this problem up for like a midterm and say, solve this problem by A, computing the electric field inside the middle body between the two objects, and then outside the two objects, and maybe even in between the inner and outer surfaces of the outer cylindrical shell. Part B, compute the voltage difference between the outer edge of this and the inner edge of that. And then part C would be compute the capacitance. Okay, that is a very typical, very wonderful, comprehensive midterm and final type question. Okay, now that we have that, we can now say, okay, well, let's use that neat new result we got, the electric field, and compute the voltage difference. So what I'm going to assume is that the let's say the inner plate is positive and the outer plate is negative. Okay, so I just said the inner plate's positive, the outer plate's negative. So in fact, if I want to make the voltage between the two plates be positive, I should integrate from the negative to the positive. Okay, so now I got to calculate delta V. What we know is delta V, which equals V final minus V initial. So I'll say V at R minus V at, oh, excuse me, that's supposed to be R1 minus V at R2. That's going to be my change in voltage. And that's defined to be negative integral E dot DL from, in this case, it's going to be R2 to R1. Okay, this time I'll let the range of integration dictate the way I'm going to go. That means my DL just has to point in the positive coordinate direction. Okay, remember that that's the decision you got to make on line integrals. A lot of times it doesn't matter if you make it or not, and you actually get the false feeling that you're doing line integrals right when you really aren't. So that's why I try to stress this every time. So I'm now going to say equals negative integral. I know that this is lambda over 2 pi epsilon naught r hat. And then, of course, the DL is actually, I'm integrating it inward. So I should have done that. But by using the range of integration to dictate direction, I'm just going to put the positive coordinate direction, which is dr in the r hat direction. And I'm going to say from R2 to R1. And remember, R2 is the bigger one. Okay, the r hat dot r hat, remember this dr can come in front of the r hat because r hats are basically dot products or linear operators, so you can pull crap out of them. Again, r hat dot r hat gives us 1, and I'm going to get negative lambda over 2 pi epsilon naught integral dr over r from R2 to R1. Okay, that ultimately should give me the integral of dr over r. Anybody know what that is? Remember, if you have to add 1 and you get something weird like 0, that's what tells you to use the len, right? So the integral of dr is going to be the len. So I'm going to say negative lambda over 2 pi epsilon naught times the natural log of r, and we're going to evaluate that from R2 to R1, which is going to be equal to lambda over 2 pi epsilon naught natural log of R1 minus the natural log of R2, which, if you remember your rules about logarithms, can be made into negative lambda over 2 pi epsilon naught times the natural log of R1 over R2. Now, R1, remember, is the smaller quantity, and R2 is the bigger quantity. And when you take the natural log of something smaller than 1, you get a negative number. So why not just make this all positive? Because that would be negative times a negative. It's going to be positive. So I'm going to flip the order and get rid of the negative and say it's lambda 2 pi epsilon naught times the natural log of R2 over R1. Again, that's just a logarithm rule. So now that I have that, I'm in a perfect spot to calculate the capacitance, and the capacitance of the cylindrical object is Q over V. Well, the Q is lambda times L, And then the V, of course, is lambda over 2 pi epsilon naught ln R2 over R1, which again, notice the charge related quantity cancels out. Like I told you, capacitance should only depend on the geometry and not of the charge. So ultimately we do get that as the case, and we see that C for the cylinders, concentric cylinders, is equal to 2 pi epsilon naught over the natural log of R2 over R1. Now, a lot of the homework problems and test practice problems that you'll run into will really just be expecting you to apply that formula, okay? And your book calculated and got the same thing I did for a similar example. Oh, the only difference is your book used RA and RB and a script L instead of a big L. But again, like I said, these problems are sort of the only ones that we can really do and solve them nice and neatly. So they're bound to be similar. But notice it didn't actually put a number by that, right? They didn't label that equation, that C equals 2 pi epsilon naught L. Oh yeah, I left off the L on this, by the way. Everybody make that correction. Make sure you write that L here, okay? Because often it's stated as capacitance per unit length. And you might notice, does anybody recognize what this object would be? This capacitor?
Is it
Daniel, I think you said it. What do you think it was, Daniel? Yeah, your speaker's not working or something. Someone else said it? Anyway?
A cylinder?
Yeah, it's a cylinder, but have you ever seen anything like that used in your house or anything? Yep. I think I heard someone say it too, Christia. It's basically the cable from your DirecTV, your dish network, or your satellite. Basically, it's called coaxial cable. There's like R6 and R59 and all that sort of stuff. And basically, what they'll have is in the middle, they often have a solid copper wire, and then they'll have some kind of almost cloth like plastic material, and they got a couple different layers of stuff for weathering issues. And then outside here they'll just have braided metal. It looks like aluminum, and then they'll put rubber around that. The aluminum is supposed to be the outer terminal, and the copper is supposed to be the inner terminal. And it's not meant to be a capacitor, but when you make things, they're going to have a capacitance, and they're going to have an inductance, and they're going to have a resistance. So you have to know how to deal with them as an electrical engineer. Therefore, they have to give you that stuff. If you actually looked up whatever company supplied the coaxial cable to you, they would give you a data sheet that can tell you how many coulombs how many farads per meter your particular coaxial cable is. And that's important, for instance, when you're running a piece of cable, say from a box on a corner to a house that might be hundreds of yards away. Does that make sense? So that's another one. But notice they didn't label that equation with any kind of number. So that's not one you're supposed to be allowed to be used generally in my class, but I will allow it, okay? I allow it. But what that means is you can put it on your equation sheet, but watch out, if I ask you to derive it, that means you better do this crap that I just did, okay? That would be the kind of thing where I'd say, okay, turn your work in at the end of the test. You got 15 minutes after your test is over, take photographs of your work and email it to me. With regards to the parallel plate capacitor, they did label that one. They labeled it 24-2, but they didn't label this one. So I don't mind you using it, especially when we're just asking simple questions like, how many coulombs will be on a cylindrical capacitor whose length is 14 meters and whose inner and outer radiuses are blah, 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 right? So I would expect you to use this instead of going through a derivation each time. But I would also advise you to go through that derivation 3 or 4 times to make sure you can do it, and maybe even do it every time just to make sure, because it should be, this explanation is long, but the actual work is straightforward and easy. You should be able to immediately apply Gauss's law, get the left-hand side, get the right-hand side, set them equal, find out the electric field, calculate the voltage, take the voltage and divide that into the charge and get the capacitance. Boom, that's the problem. That's the trend for this chapter. That's your cumulative assignment, is do that for parallel plates, cylinders, and for spheres, which I'm going to do next. So let's imagine a spherical capacitor. I'm going to say two spherical shells, if you will. One has a radius, let's say little r1, and the other one had, no, let's say, I'll go ahead and draw it. So there won't be any discrepancies of what I'm trying to suggest. Get this paper out of the way before my fan blows it. So let's try another example. Oh, I forgot to lay that one example. So that's my second example. Now example 3. So let's imagine a spherical conductor. Since it's a conductor, the charge will be automatically distributed over the outer surface, and that charge is going to be a plus Q. And then a concentric spherical conducting shell will be around it, and it will have a charge of negative Q distributed uniformly around the inside surface. Okay, I'm going to say this radius is RA, and let's say this radius is RB. Hold on a second. My daughter's calling me. She knows I'm in class. That kind of worries me that something happened. I'm just going to. Okay. All right. So we have an inner radius RA, an outer radius of the inside edge of RB. Okay. That's not supposed to go all the way out to here. I just drew it too long because my daughter was calling me. Yeah, everything's okay. Good. So what I want to do is calculate the capacitance. And again, I'm going to start with Gauss's law. The closed integral of E dot dA is equal to Q enclosed over epsilon naught. We all know that. Left-hand side, I'm making the hypothesis that E of R is equal to E of R times R hat, but this time it is spherical. So I'll put the SPH just that one time to remind you that we're talking about the spherical coordinate. And what I suspect is from the symmetry of it, for any given constant R, the electric field will be a constant. So if I come out, say, 1/3 of the distance and make a sphere, the electric field measured at anywhere on that surface of that sphere would be identical because of spherical symmetry. So the left-hand side is going to become closed integral E dot dA is equal to integral E of R hat SP dot dA R SP. Again, using spherical coordinate R hat, not the cylindrical coordinate. So it actually has X, Y, and Z. And in fact, I'm using a Gaussian surface whose radius is R. And in fact, you can think of the differential area element as being that. And of course, the electric field is parallel to that. So the E dot dA is just going to become E times A, basically, as it always does when the problems we can solve. So we end up getting E of R times the surface area of the sphere, which is 4 pi R squared. Right hand side, Q enclosed over epsilon naught. That's easy peasy. The inner one has a charge of plus Q. The outer one has a charge of minus Q. All that's enclosed is the plus Q, so that's just going to be Q over epsilon naught. So left-hand side equals right-hand side. I'm going to skip a lot of steps here. It just turns out that E is equal to Q over 4 pi epsilon naught R squared R hat. Right? Now this time I'm going to calculate the voltage delta V, which will be the V at the final one is going to be the positive one. That's where I want to make sure I go from low voltage to high voltage. So this delta V comes out to be positive. So I'm going to integrate into RA. So it'll be RA minus V at RB. Okay, so that's my plan. That's going to be the negative integral of E dot DL. And I'm going to get, say, from initial to final. This time I'm going to use the DL to dictate my direction instead of the range of integration. So I'm going to say equals negative integral. Since I'm not using the range of integration, I'm going to integrate from the small to the large, which would be from RA to RB. Yes. And the electric field, of course, is Q over 4 pi epsilon naught R squared R hat dotted with DA R hat, which again, those details you don't need to know, right? I've showed them to you. I've given them to you on my YouTube channel. You don't need that stuff. You just know that the DA comes out in front of the R hats because they're linear operators. R hat dot R hat gives you 1, the Q over 4 pi epsilon naught, and even the R squared is essentially a constant on there. But notice we actually have to calculate a DA on that same surface. So the 4 pi Q over 4 pi epsilon naught R squared all comes out in front, right? So I'm going to get, oh, excuse me. That's why I was stammering a bit there because I had written DA here and it just confused me. Okay, that's not quite right. Sorry about that. So remember, I was doing a line integral. I'd switched back to Gauss's law for some ungodly reason. So there's the electric field. However, the line integral is along a line, say from here to here. I'm just going to take it going all the way from the inner surface to the outer surface. That is in the negative R hat direction. So I'm going to write this as negative dr R hat. So I don't know why I had that brain fart, but again, this negative dr is going to come over here. The R hat dot R hat is going to give you 1. So I'll get positive Q over 4 pi epsilon naught, all of that outside of the integral dr over R squared. That's just R to the negative 2 power. When you integrate that, you get R to the negative 1 divided by negative 1. This negative and this negative already gave me a positive. So now I'm going to get back to a negative. So I'll say negative Q over 4 pi epsilon naught. And again, this is from RA to RB because I just went in the positive coordinate direction. So this is going to be 1 over RB, which is the bigger one, minus 1 over RA, which is the smaller one. So like 1/5 minus 1/3 is obviously going to be a negative quantity. So you can see immediately that's going to be positive. So we did it correctly. I can make this a little simpler by getting a common denominator. And I'm going to flip it since I want it to be positive. I'm going to go ahead and do this one minus this one and make it a positive sign. So it'll be Q, and then it'll be times, since I flipped it, it'll become RB minus RA over 4 pi epsilon naught R A RB. So that's ultimately my voltage difference. If I want to calculate the capacitance C, I just use Q over V, which means I get C is equal to Q divided by Q times RB minus RA over 4 pi epsilon naught RA RB, which again, we see the charges cancel out, so it becomes nothing but geometry. So that means C is going to be equal to 4 pi epsilon naught RA RB over RB minus RA, which is in fact the correct answer. And it is in fact positive, as we expected. Any questions on that? So that's a typical capacitor problem. Your book does a really good problem where it takes two wires. What you look at it as is, and this might seem familiar to some of us older people, but I don't think we have many of you guys in in this class. You're mostly young people. But this is what antenna wire used to look like for your TV. In fact, it had a little plastic coating that was like this, and the wires were embedded inside of it. What your book is doing in example 24.4 is calculating the capacitance of this thing. So that is an actual real physical problem, because we're dealing with literally a wire that we could still use in principle for antenna wire, and you'd get a capacitance, say, per unit length or something like that. So by all means, check that example out. It's pretty straightforward. The one thing you got to realize is when you do the voltage, you're actually integrating from a distance lowercase r. If you call that radius of that wire lowercase r, you're integrating from there to a distance of d minus r. So you got to be careful with that. And that's the mistake I normally make when I try to do the problem myself, is I always forget that I didn't integrate from 0 there. So just be careful of that, and you'll get a nice result. Y'all should be able to do that. It's really not that hard. But like I said, I'll leave it to you. And if you have any questions, by all means, ask me at lab, or come to one of my other labs and ask me then. Like, that's why I sent all you guys information about invitations for the other lab meetings. So anyone have any questions? All right, so that's sort of the robust stuff of this chapter. There's some other cool robust stuff about inserting dielectrics and creating electric fields inside the dielectric and all cool stuff like that. We'll cover that next time, but right now I want to deal with capacitors in circuits. Okay, I mentioned to you earlier, though I didn't actually draw it because I assumed you had your book with you, so you didn't have to see me draw it. But I did mention to you that the symbols for capacitor are basically this. R, I've seen it also like this. I've also seen it like this. And I've also seen it like this, if I remember correctly. I think I saw one time one do that. The main thing is these three are indicating that, hey, you need to get this type of capacitor. They'll give you the capacitance, and they'll tell you some temperature ranges sometimes, but they'll specifically say a polarity, a polar capacitor, which really fails if you connect it backwards. So that's the difference. What I want to think about is what happens when you put two capacitors in a circuit in series. What happens to you when you put them in parallel? So let me show you something very interesting about that. Let's imagine a battery. So there's a little battery. A wire is connected to it. It goes up and runs into a capacitor, C1, and then that runs into another capacitor, C2. Now I can do this for any number, but you'll see the result is generic enough that you can make it for any number, and I'll actually do that extension for any number as well. But right now I just want you to focus on that. So let's say this is a voltage V. Now what's going to happen? Well, what you know is wires are conductors, as are the plates of a capacitor. So this, again, we're imagining conventional current, which is pretending like positive charges are moving all around, when in fact we know real current is actually negative charges moving the other way. Okay, but we're always going to do conventional current. So I just want to remind you that's what's going on. So this positive terminal of this battery looks scary to all the positive free charges in this conductive wire. So the positive free charges all run around this way, this way, this way, this way, this way. And then they start to build up on this plate, and you get basically plus charges here, which I'm going to call Q. Okay. Now, those positive charges look really scary to the positive charges in this plate. So it's going to compel them to move away from that plate. And in fact, this side's going to get a charge of negative Q. Well, this thing was isolated and we assumed had zero charge initially. So you can think of it as two ways: is if this has a charge of negative Q, then this one's going to have a charge of positive Q to make it still neutral. Or you could just say, well, heck, it made the positive Q charges run this way. But either way, you still get the same answer, that this is Q again. And then these scare off the positive charges, and you get negative Q again. And in fact, the positive Qs now run around here and go back into the battery. Does that make sense based on what we learned from how charges behave and all that good stuff? So from this, what we can see is that C1 is going to be equal to the charge Q over V1, which is the voltage across capacitor 1. Similarly, C2 is going to be the same charge Q, but this time it's over V2. Okay. And since Kirchhoff's loop rule, which we'll learn later, basically conservation of energy suggests that if you go up in energy and then go down and up and down and up and down and up, if you ever end up back at the same place, the total charge or the total energy difference must be zero. So I went from here to here and jumped up a energy per unit charge. Remember, joules per coulomb is what the volt is, to positive V joules per coulomb. And then I went down V1 because I went from positive to a negative. And now I was down V minus V1, V minus V1, V minus V1. And now I go down again, this time from positive to negative, amount V2. So I've got now V minus V1 minus V2, V minus V1 minus V2, V minus V1 minus V2. And then I get to zero and I say, oh, V minus V1 minus V2 equals zero, suggests that V has got to equal V1 plus V2. Does that make sense? Because of that, we can now say, okay, I will solve for this, and I'll say V is equal to V1 plus V2. And that means that I'm going to get V1 is equal to Q over C1, and V2 is equal to Q over C2. Now, ideally, what I'd like to be able to do is replace this bank of capacitors with one capacitor that I'll call C equivalent. Okay. Well, for C equivalent, that means that it's got to be equal to Q over the total voltage, because in that case, all the charge is going to go just on it. And that charge must be Q, and all the voltage has to be spread across it, and that voltage has to be V. So I can now say, well, that's got to equal Q over C equivalent, because C equivalent has to equal Q over V. Does that make sense? So I think you can see that 1 over C equivalent is equal to 1 over C1 plus 1 over C2. And of course, if I did this with, N capacitors, it would be plus dot, 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 plus 1 over Cn. So that's the equivalent capacitance of capacitors in series. And what that tells you, oddly enough, is that whatever these capacitances are, the equivalent capacitance, meaning you could erase that one big capacitor, all those capacitors, and replace it with one quote unquote big capacitor, that one quote unquote big capacitor would have a smaller capacitance than any capacitance in the circuit. So for instance, if C1 equals 30 microfarads, and C2 is equal to 50 microfarads, and C3 is equal to, let's say, 80 microfarads, then C equivalent will be given by 1 over 30 plus 1 over 50 plus 1 over 80. Obviously, I'm going to start looking for a common denominator. The biggest number is 80. 30 and 50 doesn't go into it. So I try I try double that, which would be 160. 30 does not go into that, nor does 50. I try 240, and lo and behold, no, look, 240 the 30 goes into, and the 50 doesn't go into. So I try 320. 320 the 30 goes into, but the 50 doesn't. I try 400, and then I see finally that all of them go into that. So I'm going to say equals 1 over 400 to get 30 into, dang it, does 30 even go into 400? No, it doesn't either. Ah, crap. So 400 wasn't it. Now I'll try 6 times 80. Well, 6 times 8, of course, is 48. 30 doesn't go into that. 7 times 8 is 56. 30 doesn't go into that. 8 times, well, it looks like we're ultimately just going to have to multiply 8 times 8. 8 times 8, of course, is 64. So I'll say 640. So we'll put it all over 640. To get 640, I got to multiply 3 by what? 3 goes in 60 20 times. Ah, crap, that didn't work either. Dang it. Son of a... Okay, so it's not 340. I tell you what, I'm going to use my calculator because it appears that my quick arithmetic is going to go really badly, really quickly. So I'll just use my calculator and say that the ultimate answer is I'm working on it. Plus still working on it. Hold on, folks. So that is 65.833 times 10 to the negative third. And that's 1 over microfarads. So that means C equivalent well, I really did a horrible job on that. Anyway, C equivalent is going to be 1 over that. And that's 15.19 microfarads. Notice that is in fact smaller than each individual capacitance. That was what I was trying to stress. When this formula comes up, you get a result that's always going to be smaller than any one of the single results. So the equivalent capacitance to replace 3 in a circuit is actually going to be smaller than the 30, the 50, or the 80. Okay. Now, class is about over, but let me quickly do this other one just so you can get started on some stuff. When you have the battery like this, and then you have a capacitor here and a capacitor here, C1 and C2. Well, this is a little different scenario because the battery is going to let out a charge Q. And then some of that charge Q1 will go to this one, and some of that charge Q2 will go to this one. But Q has got to equal Q1 plus Q2. Now, because it's in parallel, we know that basically this voltage is the same as this voltage is the same as this voltage. So V1 is equal to V2 equals V3. You can sort of think of it as this battery brings you up to a hill's height, and then there's no resistors, so the hill height doesn't decrease in going to here or here. So these all are at the same height. That's why the voltages are all the same. Or excuse me, V, just plain V without the V1, without the V3, excuse me. So the voltage of the battery is equal to the voltage of each of them. And then I see that C1 is equal to Q1 over V, and C2 is equal to Q2 over V. Plugging that into here, I see that C1V is equal to I see that C equivalent times V, which is this side, is equal to C1V plus C2V. The V's cancel out, so C equivalent for parallel is equal to C1 plus C2 plus dot, dot, dot on up to Cn. This was for series, and this was for parallel. Okay, so now you have the result for when you put a bunch of capacitors in parallel. It turns out the net capacitance, like if I wanted to replace this whole bank of wires right here with one wire and one capacitor, the net capacitance would just be the sum of them, which obviously is, for the case we did, would be 160 millifarads. You folks are free to go. Thank you for staying, and I should have these notes and the video posted later on today.
Have a nice day, Professor.
You too. See you, Clarence. See you, Jared. Anybody have any questions? I'm sticking around in case you do. Austin, do you have any questions? You get your stuff done? All right, looks like everybody's done. See you guys. Thanks, Christian. You were right. It was 1200. I don't know what I was thinking. Okay.